Hello everyone. I hope all of you are doing very well, and I guess most of you might have already gone through my previous lecture wherein I discussed about the basics of carbohydrate chemistry and how are we going to actually convert an open structure to a ring. Correct. I have also given you the mechanism, what exactly happens, what are the different ring forms or ring structures, that is pyranose and furanose. Now the question is, when I discussed the mechanism, it was pretty much easy to understand. But in that mechanism, I was only concerned about closing the ring, right? Closing the open structure to form a ring. But I didn't bother about taking into account what happens to the other groups and how you're supposed to write. When you have a ring carbon, how are you going to represent the groups, right? So how carbon is tetravalent. So which are the groups that are going to be at what position? This is something that might be striking in your head. Okay, so before actually getting into the actual structure of carbohydrate, now let's try to understand one very important concept. This concept is going to be the essence of what exactly you will be studying, because without this you cannot actually proceed for the structure, and believe me, it's one of the easiest thing to do. Okay, so we are basically going to discuss about the Fischer projection conversion to Haworth projection. We already know that in Fischer projection you have a horizontal line and a vertical line, right? And then horizontal lines, they are the ones which are pointing towards the observer, and vertical lines, they are the ones which are pointing away from the observer. So exactly like the wedge dot formula, I think I have already discussed this clearly in the basics. Okay, now you are supposed to transform this open structure into a ring structure. Now there are certain rules that we are going to discuss. Okay, so this video is going to be interconversion of Fischer projection to a Haworth projection. Okay, so let's try to begin with this discussion. Okay, so I've just kept this as a very simple part. Okay, so let's try to just have it in terms of something like differentiating point. Okay, so let's try to do the distinguish between, right? So you have the Fischer projection and then you have the Haworth projection. So what exactly is going to happen over here? So you already know that in Fischer projection you have the horizontal and the vertical line intersecting at a particular point, that's called the chiral center, right? So you have the vertical line and then you have the horizontal line, right? So now I'm going to concentrate on maybe like 3 to 4 chiral centers. Okay, or maybe let me just draw a smaller molecule. I think that's much better to okay, just a second. So I'm just going to draw a very smaller molecule so that you are able to understand what exactly is going to happen over here, right? So I'm going to draw the structure of a glucose molecule, right? So it's going to have one, then you have two, and then you have the third one, correct? And then you have the fourth one, right? So let me not exactly put the structure of glucose, let me just put randomly the groups. Okay, so this is CHO, this is CH2OH, and now I'm going to randomly put the groups over here. So this is going to be OH, this is going to be OH, this is going to be OH here. Now again I'm telling you, I'm just randomly placing the H and OH in this. Okay, so if you could see here, this is an open structure. Now I have to convert it into Haworth projection. So Haworth projection is basically something which you call it as the boat form, right? Wherein you transform this into a pattern in which it's very easy to convert it into a ring structure, right? So there are certain things that you should remember, right? And the first thing is, right, so you have to convert Fischer projection to Haworth projection. So I'm just going to write this. The group is which is at the right, okay, the group which is at the right position in Fischer, right, position in Fischer is going to be placed downwards, okay, in Haworth or Haworth, whatever you call, okay, in this Haworth projection formula, right? So what exactly is going to be your Haworth projection formula? Now I'm going to write this in terms of a boat form, right? So this, if you could see here carefully, I'm just trying to make a six-membered ring. Correct. So if you could see here, this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Now we already know that, each carbon is tetrahedral. So I'm going to place something over here. Correct. So if you could see here, the carbon is tetrahedral, that I have already mentioned over here. Now if you already know this is, let's try to number this. So this is 1, this is 2, this is 3, this is 4, and this is 5, and then this is sixth carbon. So here I've already said that topmost is going to be high priority, right? And this is going to be low priority. So you have 1, you have 2, you have 3, you have 4, and then you have 5, and you have 6, right? So if you could see here, this is the first carbon. So I'm going to write here as CH and then double bond O. Okay, I hope up till here it's completely clear. What exactly I've done? I've just bent the molecule so that I can transform it into a ring structure. Correct. Now at position 2, if you could see here, the OH group. Now if you could see here, this is left side and this is right side, right? So OH is at the right, and what exactly happens to the group which is at the right? It's going to be down in Haworth, right? So it's going to be OH over here. At position number 3, again it is at the right, so it's going to be down. At position 4, H is there, right? So it's going to be H here and OH is going to be up, obviously. And this group is going to be here, right? Correct. And then at the position 5, there is HH. Okay. So basically, let me just make this little bit different so that you don't get confused. Okay. So what exactly I'm going to do here is, I'm just going to rub this out. Okay. And then I'm going to make this as an OH. Correct. At position number 5 also, you can see right, that is going to be down. So I would recommend one thing, that just remember, write down. Okay, what does that mean? The group which is at the right is going to come downwards. Okay, this is basically conversion of a Fischer projection to a Haworth projection. Okay, now let me talk about the group number 6. This group number 6 is nothing but CH2OH. Correct. Now if you could see here, it's pretty much easy to convert this into a cyclic form, right? So how exactly we are going to do this? Now that's going to be very interesting, and I will be discussing this exclusively in the next video, wherein we will be doing different structures of glucose and fructose, how the mechanism is going to operate, and how you're going to write the structure in a wonderful manner. Okay, so this is basically the interconversion of Fischer projection to Haworth. Okay, so this is basically very simple to understand. Okay, so the keyword that you are supposed to remember and memorize and never ever forget is R down. That means the group which is right in Fischer is going to be downwards. Okay, right, and obviously let me complete the structure. So the unfilled positions are obviously the hydrogens. Okay, so this is basically the interconversion of Fischer projection to Haworth projection formula. Okay, now you can also convert this into a chair form. You already know that there are two different forms, boat form and chair form, but for conversion of chair forms, you are supposed to understand the axial and the equatorial bonds. So definitely I'm not going to discuss that, because that's little bit of a higher level. Okay, maybe in the next couple of videos I might try discussing all this, or I may make a separate video regarding the boat and the chair forms of a particular cyclic compound, especially the cyclohexane. Okay, but anyway, we don't need it when we are discussing the carbohydrates chemistry, basically the structures of monosaccharides and disaccharides. Okay, now the question is, why did I make this video a separate video? Because you have to understand, this is a very basic thing which you need to remember if at all you want to draw the structure of any of the monosaccharide. Okay, so this is all about, I've just taken a random carbohydrate. Okay, now what I'm going to do here, is I'm going to take a specific carbohydrate and convert it into Haworth projection. Okay, so this was all about the Fischer projection to Haworth projection interconversion. Okay. So let me just move on to the next part. So we are going to start with the example of D-glucose. Okay, so I'm just going to modify the structure. I'm just going to erase the things which are actually not needed. Okay, so what I'm going to do here is I'm just going to erase these ones. Let me erase the numbers as well. I just need to get a horizontal and vertical framework. I'll just erase the functional group as well, correct? So I'm just going to have these things on the screen right away. Okay, so now what exactly I'm going to do here is I'm going to draw the four chiral centers, correct? So this is basically the four chiral center, and now I'm going to draw the structure of D-glucose. So D-glucose, it's an aldose, so you have CHO group here, and this is going to be CH2OH, correct? Now you should remember in the case of glucose, okay, so this is the first carbon, this is the second carbon, this is going to be the third carbon, right? So it's going to be like third carbon is going to have, the third carbon is going to have OH on the left side, right? So second carbon it's on the right, fourth carbon on the right, fifth carbon on the right, and sixth carbon is already CH2OH. The only thing is this third carbon is going to have OH towards the other side. Unoccupied positions or unfilled positions are hydrogen. Okay, so now what I'm going to do here is I'm going to erase all these, okay, and then I'm going to erase this as well, this, okay, let me keep the bonds intact at least, okay, so I'm just going to get rid of these groups, okay, cool. Yes, so that I can actually transform the structure much easily. Okay, so this is basically the form which I'm actually discussing, correct? So now let me put down the numbers. So this is number one, this is number two. Okay, what I'm going to do is let me delete the numbers because I'm writing it fresh. Okay, so you have number one, number two, and this is number three, this is number four, and then you have the fifth carbon and the sixth carbon. And now what I'm going to do is very simple. I'm going to draw the tetrahedral carbon, satisfy all the valencies, correct? So now let's have a look. Number one is CHO, so I'm going to write here, either you can write it as CHO. I'm going to be a little bit more specific, writing the functional group, the proper structure. So if you could see here, 2 has this OH towards right, so this is going to be down, right? Now in the case of third one, it's going to be H down and OH is going to be up, right? In the case of fourth one, then it's going to be down as well, right? So please have a look, RD, right, down, right? And then you have fifth carbon has OH on at the bottom, or you can say down, right? The unoccupied positions, or you can say the empty spaces, are basically the hydrogen, and the sixth carbon is not chiral, so this is nothing but CH2OH, right? Correct. So this is a very simple way to convert a Fischer projection to a Haworth projection. I hope this becomes very much clear, because if you are clear with this particular concept, then you know, drawing the structure of biomolecules, you will not find any sort of discomfort. Okay. So this was all about the examples, like conversion of, you know, Fischer projection to Haworth projection. What is the keyword that you are supposed to remember? The group which is on the right side in Fischer projection, that this is going to be coming on down, right? This is going to be coming on the bottom of the like of this framework, or you can say this is going to be downwards. Okay, so right, it's going to be downward. That goes without saying that left has to be upward. The one which is on the left is going to be definitely up, right? I hope this video is clear to all of you. Now if you have still any confusion or query, you can just try revisiting the video, and once you master what exactly I've told right now, it's very easy for you to do the conversions in the later stages. Okay, so you need to be a little bit patient and then practice a lot and then get on to the structure. I hope this video was useful. Now in the next video, we are going to talk about the structures, the pyranose and the furanose structure of glucose and fructose. So basically we'll be dealing with monosaccharides at the moment. Okay, thank you.